Introduction to Molecular Orbital Theory, Part 3, Homonuclear Diatomic Molecules. Okay, so let's just remind ourselves of where we are. We're talking about molecular orbital theory, or MOT. It's a delocalized model, and so bonding electron pairs are delocalized over the entire molecule. That means that there's no need for resonance structures like we need in the localized electron model. Now, another aspect of MOT that I don't think I've stressed quite enough is that MOT can describe bonding in both ground and excited states. Now, the localized electron model can only describe bonding in the ground state, so this is another clear advantage for MOT. Now, so far we've seen the 1s orbital mix to form two new molecular orbitals. It makes the sigma bonding 1s molecular orbital and the sigma 1s star antibonding molecular orbital. Now, what we haven't seen is that MOs can also be formed by mixing p orbitals. Now, there's a few extra rules that goes along with mixing p orbitals, and one of them is that they have to have the same orientation and similar energy, and then they'll mix. So, for example, the px orbital on each atom in a diatomic molecule will mix to form a bonding and an antibonding MO. So you mix two atomic orbitals, you get two molecular orbitals back out, a bonding and an antibonding. The py and the pz orbitals also mix in the same way, so they mix with each other. Py mixes with py and pz mixes with pz. Okay, so we're going to see two different MO correlation diagrams for these second period homonuclear diatomic molecules, and they're slightly different. So for first order, so it's going to be used for oxygen, fluorine, and neon, and then all of their associated ions. And the second order diagram is going to be used for lithium, beryllium, boron, carbon, and nitrogen, and then all of those associated ions. So for instance, we could take a diatomic lithium molecule, give it a plus charge, and that would be one of these ions that we'd use a second order MO correlation diagram for. Okay, so here are the two correlation diagrams. So one on this side, I'll say more about these in a second. That's the second order, and here's the first order. Okay, and so these are two separate diagrams. They are on the same page, so don't get confused. Now, down here at the bottom, we see 1s atomic orbitals. That's what AO stands for. So just looking at this one, the 1s mixes with the 1s to form a sigma 1s bonding MO and a sigma star 1s antibonding MO. And notice also that, as before, the sigma 1s MO is lower in energy than the atomic orbitals are separately. And so that's very favorable. Now, notice that it says core down here. So for second period elements, the 1s, those would be core electrons. And usually when we're talking about MO and correlation diagrams for second period diatomics, we tend to ignore that core electron part of the diagram. Sometimes it's there, sometimes it isn't, so you do have to look. But most of the time we're going to ignore it. Now, once you do that, then you're going to deal with just the valence part of the diagram. And so valence electrons in second period diatomics are going to be found in 2s and 2p. Now, remember, when you're filling in electrons, like we did with the hydrogen diatomic MO correlation diagram, we counted up all of the electrons. Well, now we're going to start counting up valence electrons when we use the valence molecular orbital correlation diagram. Now, one more thing that I want to point out here is that these things are virtually identical, the first order and the second order, except inside this box. So you can see that the sigma 2pz and the pi 2px and the pi 2py, you can see that those are swapped in energy. So that's the only difference between the two correlation diagrams. Okay, so before we go on, let's just talk a little bit more and make sure that we know what's going on with these diagrams. So again, I'm just going to look at the second order, but everything I say also goes for the first order. So we're going to take the 2s atomic orbital on each of the atoms in the diatomic molecule. We're going to mix it. Going to get a sigma 2s molecular orbital and a sigma star 2s molecular orbital. So mix 2 atomic orbitals, get 2 molecular orbitals back out. The p's are a little bit different because let's say that we make this the 2px. Okay, so that one's 2px and it's 2px here on this side. So if we mix those two, we're going to get a molecular orbital, and that is going to be a pi 2px. So that's a pi 2px molecular orbital, and its antibonding counterpart is going to be up here, the pi star 2px. So px mixes with px to form a px molecular orbital, a pi 2px. Same thing with pi 2py. So we take the py from each atom, mix those two guys, and we're going to get a pi 2py, and of course the counterpart up here, the antibonding molecular orbital, the pi star 2py. And then finally, 2pz can be right here, so those have the same orientation. Mix them in a head-to-head overlap, and we're going to get a sigma 2pz molecular orbital, and then of course there is the counterpart, the sigma star 2pz. And so basically nothing has changed from our hydrogen diatomic except that now we have a lot more atomic orbitals to work with. Notice this middle column, this is the molecular orbital column, and you'll see later on that sometimes we just leave this other part off and we just draw these in order of their energy. Okay, so just a little reminder, sigma is a head-to-head overlap between orbitals in a sigma bond. And so 2s atomic orbitals are going to mix to form the sigma 2s bonding MO and the sigma star antibonding MO. And now these MOs look really similar to those formed by mixing 1s orbitals, except for the radial node, which is not going to be shown. So what I'm actually going to do is just remind you of this mixing on hydrogen. So this is the 1s on one hydrogen, the 1s on the other. And we're going to mix, overlap, they both have the same phase, so they have constructive interference, and we're going to form the bonding molecular orbital. The sigma 2s bonding MO looks really similar, but it has a radial node on each side. Now we're not going to get into that, but the overall shape is very similar. Now what about p orbitals? So they're kind of interesting. So we're going to take the 2pz atomic orbitals, we're going to mix those. So here's one of them, 2pz, here's the other one, and we're going to mix. There's orbital overlap. We're going to form the MO, and so here's the sigma bond, and then here's the other lobe on each of the p orbitals. So it's a head-to-head overlap, and that makes it a sigma bond even though it's a p orbital, or a 2 p orbitals, I should say. Okay, so this side-to-side overlap. So if we want to form pi molecular orbitals, we're going to have a side-to-side overlap. So here we have 2px and 2px. Okay, we're going to overlap, and our little cartoon molecular orbital is going to look like this. So these two are going to kind of merge, shall we say. And then here are the two nuclei in between. I don't have them pictured, but that's where they are. Then there's electron density above and below. And so this is a side-to-side overlap of these 2px orbitals, and they form a pi 2px molecular orbital. Okay, so let's go back to the first order correlation diagram. And I just want to also point out again that this sigma 2pz is lower in energy than these pi molecular orbitals. So basically there's better bonding with sigma than pi due to better screening of nuclei by electrons. So it's lower energy. Okay, so now let's talk about molecular orbital bond order and electron configurations. So remember from our hydrogen diatomic discussion that we could write a MO bond order, we could calculate that, and we could also figure out the electron configuration by writing down which of the MOs are filled and with how many electrons. So let's go ahead and do an example of that. Okay, so now first thing we notice is that we have the valence molecular orbital correlation diagram, and we have the first order diagram because we are working with oxygen. And so we use the first order diagram for oxygen. Now, we want to determine the number of valence electrons. So if we count up for O2, we're going to get 12. And we have our diagram. So we are set to fill electrons. So let's do it. So we're going to use orbital filling rules. We're going to start at the lowest energy, the sigma 2s, and we're going to fill 2 electrons in an orbital and go up in energy. So 2, 4, 6, 8, 10. Now, we're going to end up with unpaired electrons in these pi stars, and so we're going to use Hund's rule. We're going to put them both, each in their own orbital. Okay, so we're going to not pair them, and they have the same spin. So that's following Hund's rule. Okay, so let's calculate the bond order. Now, what we're going to do is use the same equation as we did before, except now we're going to have to count quite a few more electrons. So let's go over here, and so remember, its bond order is 1/2 of the number of bonding electrons minus the number of antibonding. So let's count up our bonding. So 2, 4, 6, 8. Okay, so 8 bonding minus 2, 3, 4 antibonding. Divide that by 2, and we get a bond order of 2 for O2. And that matches the Lewis structure. But notice that MOT correctly predicts these unpaired electrons. So remember, when we started this discussion, we said that oxygen must have unpaired electrons because it's paramagnetic and it's attracted to a magnetic field. So experiment demonstrates that, but we didn't have a way to show that electrons are unpaired in the oxygen molecule until we started working with MOT. And so we can see that molecular orbital theory does correctly predict that. Okay, so let's write the valence molecular orbital electron configuration. So this is very similar to what we did before. The sigma 2s has 2 electrons in it. The sigma star 2s has 2 electrons in it. The sigma 2pz has 2 electrons in it. Let's write down our pi's. So there they are. Now sometimes you'll see this as pi 2px comma y, and there will be 4 electrons in it. And that's a little bit of a shortcut, but that's okay to do. You'll see that, and that's okay. And then these 2 guys up here, it'll be pi star 2px with 1 electron and the pi star 2py with 1 electron. Again, for experienced people, you might see 2px comma y with 2 electrons in it, but an experienced person would know that there are indeed unpaired electrons in that, where it might not be obvious if you write it that way. Okay, so what's our procedure for determining the molecular orbital bond order and configuration? First, we're going to determine whether the first or second order correlation diagram applies. The second thing we're going to do is count our valence electrons, and we're going to fill the MOs. And we're going to begin with the lowest energy, and we're going to use our orbital filling rules. So we're going to use the Pauli exclusion principle. No 2 electrons can have the same 4 quantum numbers, so they have to have opposite spin if they're in the same orbital. We're going to keep them unpaired unless we have to for degenerate orbitals. And we're going to fill from the lowest energy to the highest energy. Now we can calculate bond order and electron configuration using the correlation diagram. Alright, so next up we're going to do the exact same thing for heteronuclear diatomic molecules.